This is the SOLIDWORKS design project of the Mars Ingenuity helicopter for the DFT170 Engineering Graphics class in the spring of 2023. This is presented by Andrew King, Benjamin Laterio, and Harry Anderson. We were instructed by Dr. Hans Chapman during the making of this presentation. This is the reference model that we use to create our sketches and our models. In this image, you can see the basic parts that we would need to create our assembly. First being the legs, then the fuselage, the base the wings were attached to, the wings themselves, and the solar panel on the very top. At this point, we began to brainstorm ideas on how to accomplish our goal. These were our preliminary hand sketches of the parts that we would need to model. From left to right, you can see the landing gear, the solar panel, the drone fuselage, and then a rough sketch of our completed assembly featuring the legs, the fuselage, the base, the wings, and the solar panel.
Here we have the fuselage. The fuselage is the main body of the drone, which contains parts such as the engine and controls. In order to model the fuselage, we first extruded a box and then used the fillet tools around the edges. From there, we were able to attach the logo. Next, we have the legs. The legs are used for stability, as well as act as landing gears. In order to model the legs, we first sketched a curve using the line tool and fillet tool. We then used the swept boss base tool to add a body around the curve. Then we have the wing base. The wing base acts as the pivot point for the wings to rotate around. To model the wing base, we sketched one side of the upper half and one side of the lower half, then used the revolve boss base tool to create the bodies, allowing each half to pivot on their own. Here we have the wings. The wings rotate at high speeds in order to create an upward lift in order for the drone to fly. To model the wings, we sketched the edges and used the lofted boss base tool to form the shape. We then used the extrude boss base tool for the connection point and the mirror tool for the reversed wings.
This is a screenshot of our final assembly. We were able to use parallel, coincident, and concentric mates to ensure that all the parts fit properly together and with correct clearances. This is our drawing document, complete with front, top, right side, and isometric views. This is our simulation. We chose to do a simulation of just one of the wings to see how it would handle the stress under load that it would have during flight. As you can see, there's a significant amount of stress shown by the red coloring near the base of the wing. We would need to strengthen this part of the wing to ensure that it doesn't fail while the helicopter is flying. This is our animation, and as you can see, both of the wings are able to rotate independently from one another and in both directions without making contact.
In closing, our team had to learn to rely on one another to complete work on time. To succeed, it was important that we were able to communicate effectively, and of course, keeping team members in check with their responsibilities was key to our timely success. This would have been a very, very difficult task for one single team member, and much stress was relieved by relying on one another and trusting their capabilities.